This video, we're going to look at an implementation of a set using bit manipulation, and I'm going to call it the BitSet class. So first of all, I've got my project all set up. Let's look at the design of the BitSet class. So first and foremost, we've got our private data members. I'm going to use capacity or cap to tell me how large of an item I can store in my set. Size is going to be the number of items in my set, and then bits is going to actually be the unsigned integer that I use to encode the presence or absence of elements in my set. Then starting with the design, there are a bunch of other methods you could add, and we're not going to implement all of these, but this just kind of gives you a sense of the types of operations that we would probably want to have in a set abstract data type. So clearly we have to be able to add elements. Maybe we want to know what the cardinality or the size is. Capacity will tell us what the upper limit is. Certainly we want to be able to clear if we want to remove all of the elements of the set. Complement, compute the complement of the set. We need to know if the set contains a particular element, whether the set is empty, and then we have our classic set operations like difference, intersection, union. This tells us if one set is a subset of the other. We want to be able to remove elements. Maybe we want to know, if two sets are equal, things of that nature. And then size is just another method that returns that's equivalent to the cardinality. Now, one thing I've already done is I have copied an implementation of Wegner's algorithm. I've named it's a private method called set size, and I'll show you why we need to use it and how we're going to use it. So the first thing I'm going to do is I'm going to start off with my default constructor, and I've already stubbed out some of the methods that we're going to implement in the video. And so the things that I have to set are size, capacity, and the bits. Well, bits, that's easy because I just use the unsigned integer 0, and then size, if I have an empty set, it's also going to be 0. Now, to figure out the capacity, I have to take into account, remember that bits is an unsigned integer. And so I need to find out how many bytes this computer uses, or this C++ platform uses to store unsigned quantities. And I can do that by calling the size of function. And I know that bits is an unsigned, and that's going to give me the number of bytes that we're using to store unsigned quantities. And then I know that there are 8 bits in each byte. So this is going to tell me the capacity of my set. Now I'm using an unsigned. We could use an unsigned long. We could use long, and reach higher capacities. But for this demonstration, we're just going to use a plain old unsigned. So now this is going to construct an empty bit set for me. All right. So I can, now if I go into main.cc, I've got some test code here where I just call my default constructor. Let's see if this compiles. It does. It's going to run. It's not going to do anything. And now in terms of checking to see if my bit set is empty, again, I just stubbed this out. How do I know if it's empty? Well, it could be that I could check bits, because if there's 0, that means there's nothing in there. Or I could just use size being equal to 0. So I'm going to use size, and so I can just return whether if size is equal to 0. If that's true, then I know that my bit set is empty. The size method is also easy. All I have to do is return size. Capacity, I would just return cap. Cardinality, I would return size. And so now let's look at an implementation of the contains method. And I'm going to switch over to the whiteboard function to illustrate how we're going to implement that. So if we're looking at an implementation of contains, and let's say that this is my set, and I have zeros, and then somewhere I have a 1, and more zeros, and then some ones. And let's just say that this is element 12, right? So that means that 12 is in my set, and I want to find out if that value is in there or not. And what I can do is I can set a mask. I'm going to, and of course we have zeros through here. And I set my mask up so I have a bit in the first position. And now I shift it 12 spots to here. And now this is 0. This all gets padded in as 0. And so I'm shifting it over 12. This is my element that I'm looking for. And now I can perform a bit operation on between the mask and the set. And if that bit operation is true, then I know that the element's in the set. And I'm going to use AND to do that. And because I have zeros everywhere else, these operations will result in 0. So that's how we're going to implement contains. So to implement contains, first thing I'm going to do, and we could do a range check. I mean, we know that element can't be greater than whatever capacity is, but let's skip the range check for this. And I'm going to set up my mask, and I want it to be start at 1, but then I want to shift over element times. And so that's going to position a bit where the corresponding element will or will not be in our set. And now I just need to do an operation between the bits and the mask. So I can just use the bitwise AND operator, and I want to return this. And just to make it a bit cleaner, I'm going to return the static cast because I want this to be a bool between bits and masks. So this is going to give me a 0 or a non-zero value. This operation is going to give me some unsigned, and I'm just going to cast that to a bool because that ultimately is my return value. So make sure that compiles. It does. We don't have any way of testing contains because I haven't implemented a method that would let me add an element to the set. So let's go look at how we're going to implement add. Okay, so to implement add, we're going to do a similar type of scheme that we did with contains. We're going to create a mask. We are going to shift a bit to the proper location, and then we want to perform a bitwise operation that will actually set the bit in our bit set. And then of course we want to increase size. There are a couple of other little details that we need to work out in add, but right now I just want to demonstrate how we're going to add something. So with add, I've got my set. Well, it's actually called bits now. I guess I should start using that. And let's say that there are some other bits. And I want to set this element. And let's say that element is 22. I want to turn element 22 on. So what I can do is I can create a mask, and again I'm going to set the first bit to 1, and then I'm going to shift it over 22 bits, and now I'll have a 1 here. Whoops. And zeros everywhere else. And I need to perform an operation that will give me a 1. And you can see that OR will do that. So if I OR these two values together, I get a 1. But then I need to store that bit in bits. And so the assignment I can use for that, and we covered this in an earlier video, I can just say bits and then OR it with mask. And that's going to give me a 1 where I want it after I change mask. Just like this. And in doing so, I have added 22 to my set. So let's go look at how we're going to implement this. Okay, so some of the details that we didn't discuss in terms of implementation. Well, let's first of all just put in the code that we need to add something, and then we'll fix what we need to do. So first thing I need to do is I need to create my mask, and I can do that by shifting a bit element times, and then I can change bits by ORing it bitwise OR with mask. And then I'm going to go ahead and use the additional assignment operator to make this just a little cleaner. And now that I've added a new element, I need to increase the size by 1. Now, one problem with this implementation, so first of all, let's compile it. And maybe I'll go into main and I'll add 0. See if this runs. It does. Maybe I can say if BS contains 0. Just to do a quick little check here. All right, so 0 is in there, and then if I put in some other value like 2, I should not see any output at all. Okay, things seem to be working. But one of the problems is with that implementation. Let me see, did I implement size? Because that would let us. I did implement size. Okay, so here's the problem with that implementation. Let's say that I add 0. Now 0 can only be present once because this is a set. Remember that a set contains only distinct objects. And so if I print size the first time, it's going to be right. So you can see that after the first add, it's correct, but then it keeps increasing size. So that's the problem with our add method. So what we need to do is we need to see if something is already in there. So if the set already contains the element, then we don't want to do anything, right? So if it doesn't contain the element, then that's when we know that we want to add this to our set. Just like that. Now let's run. Let's compile. And again, remember what main is doing is we're doing these 3 adds, and now if we implemented it correctly, we'll see that size is 1 with both output statements. Okay, great. So now the next thing that we need to fix is we know that my capacity of my set is 32, but what if I try to add something like 1,000? So I need to throw out of range and I can do that by checking to see if element is greater than or equal to capacity, right? So capacity is going to have 32 in it. I can store 0, so my set can store the value 0 through 31. And I just want to throw out of range. And this is defined in the standard template class or standard template library. And just a little helpful message there. See if this is compiled. And I can't remember if I don't have any try blocks. So let me add a quick try block here. And we'll catch out of range. And I'll just do a quick output here, nothing fancy. And fix this code. All right, let's see if this compiles. And now I should see, if I look at main again, so I should see 1, and then this should throw out of range, and I should see out of range, and I won't see this cout. Right, that's what happens. Okay, so I'm successfully doing my range check, and let's just go back and look at how we implemented this add method. Right. So we do our range check, make sure the element's not in the set, and if it isn't in the set, then we add it, we increase size. Okay. So the next operation we're going to implement is set union, and let's go back to the whiteboard function and I'll show you how we're going to implement that. Okay, so you remember that the union operator is the joining of two sets. So if I have 2, 3, 4, and I union that with 3, 7, then I get 2, I get 3, only one copy of 3, 4, 7, right? So in terms of bit operations, I've got some bits that are on, some bits that are off. Don't really care at this point what elements these bits correspond to. And so, this is going to be, coming in, and this is going to be coming in as a parameter bit set, and the set on the left is going to be this bit set. So I've got this bits, and then I've got bs.bits, and they're going to be something like this. And then I want to perform an operation that for every 1 that might be present in either of the sets, I need to get a 1 in the result. And that is just the OR operation. So I'm simply going to use bitwise OR on these two unsigned integers, and then I'll store the result in this bits. So I can just write bits just like that. So that's the heart of it. Now, here's the tricky thing is, what about size? And so you can't figure out size by just looking at the sizes of the respective bit sets, because you don't know where they do and don't overlap, right? So if we knew that the sets didn't overlap, we could just add size together, the two sizes together. But we can't do that because we don't know how many bits or how many elements of these sets are in common. So we have to count the bits after we perform a union. And in the previous video, we looked at a method for doing that. I'll go back over it, but that's how we're going to figure out what the new size of our bit set is. Okay, to implement set union, let's take a little trip down here. So this is the set size method that I'm going to take advantage of. And I went over this in a previous video, counting bits. And so I just took that, since it destroys the number n, then I have to set bits to this local variable. And then I'm just declaring a local size so it's not interfering with this size. I guess I could just use this size if I wanted to, but I used a local variable instead. And then this gives me the new size of my bit set. So now to implement set union, all I have to do is perform bitwise OR between these two bit sets, and that gives me the set union. And then I need to set the size. So that's the implementation of set union. Now the other thing that I did down here is I implemented a stream insertion operator, and so this just prints a bit set in the format that we expect. So now let's go back to main. Let's see if this compiles, and now let's go back to main and test some of the methods that we've implemented. So we know that these work, and so now I can print out what my set looks like. I know that contains works. So let's see if my print statement or my stream insertion operator is working. Yeah, so that prints 0. So now let's create a couple of different sets, and then we'll try set union and see if it works. All right, 0, 3, 5, that looks good. And then I can just copy these lines here, and maybe I'll call this BS1. And maybe I'll add in some different numbers here, 10. Zero, 3, 5, and 10, 13, 15, and now let's union these two together. One thing I'll do is maybe I'll create a third one for that. So I can use the copy constructor to construct a copy of BS1. So maybe I'll see out BS2 here to see if I've got a copy. And notice that I didn't implement a copy constructor, but I still get a copy constructor. And when you have a default copy constructor, and it is perfectly fine when you have a class implemented using the fundamental types, and so we're using 3 unsigns, or if you have a class that has a copy constructor like a string or something. So now I've got BS2, and I am going to now union BS2 with BS1. Oh, I'm sorry, with BS. And then we'll look at BS2 again. So I should see the set with all of the elements 0, 3, 5, 10, 13, 15. And that's how I'll know that my set union is working. All right, so there you go. Here's my first set, here's my second set, and here's the union of those two sets. Okay? So now your homework is to flesh out the rest of these implementations. So complement is easy. You just need to think a little bit about how you're going to get the new size. Intersection is easy. It's going to look just like set union. And again, we're going to take advantage of set size. We need to be able to remove elements from a set. Think about what bitwise operator will let you do that. And then you can also implement subset. And with that implementation, you'd have a pretty nice set ADT.